Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video we shall be discussing about semiconductors. So relax, do not go anywhere and I will be right back. You are welcome back to my school YouTube channel. Like I said earlier, in this video we are going to be learning about semiconductors. Okay, so but before we begin with our lesson, let's quickly run through the objective for today's video lesson. So objective number 1, distinguish between conductors, semiconductors and insulators in terms of their conductivity and mode of conduction. 2, explain the two types of carriers of electricity in a semiconductor. 3, distinguish between the N-type and P-type semiconductors. 4, describe the P-N junction diode and its current voltage characteristics. And 5, discuss the use of a diode as a rectifier. So let's kick off with our lesson. So here basically we are going to be looking at the meaning of semiconductor. Okay, so semiconductors are materials whose electrical conductivity is intermediate in value between that of good conductors and that of insulators. Okay, and some examples are germanium, silicon, etc. Of course, these two are the most commonest example. Okay, so semiconductors are widely used in the electronics industry, in computers and communications. So semiconductors have a crystal structure. They have 4 electrons in their valence or outermost shell. Okay, now let's talk about the charge carriers in semiconductors. So in metals, for example, the charge carriers are only free electrons. Okay, and the charge carriers in semiconductors are electrons, that is free electrons, which have negative charges, and holes which have positive charges. I think this is the major difference between a metal and a semiconductor, okay, in terms of the charge carrier. Okay, so for a metal, the charge carrier is only free electron, but for a semiconductor, the charge carriers are free electrons and hole. Okay, so this is the diagram of a semiconductor showing the holes, okay, and the electrons. So remember, the holes are positively charged while the electrons or the free electrons are negatively charged. Okay, so let's move over to the next slide. So the free electrons and holes, they move about randomly in different directions inside the semiconductors. But when a battery is connected to the semiconductor, the free electrons move in the direction opposite to the electric field, while the holes drift in the direction of the feed. Okay, thus the current in a semiconductor is carried by free electrons and holes. Okay, so let's look at this part. Free electrons move in the direction opposite to the electric field. Now remember, the electric field begins from the north pole, okay, and ends in the south pole. You get? So what they are trying to say in essence is that the free electrons, okay, move in direction opposite to the flow, okay, of the electric field. That is, move towards the north pole, while the holes drift towards the south pole, which is actually the direction of movement of electric field. Okay, so thus the current in a semiconductor is carried by free electrons and holes. So you have to take note of that. So in a pure semiconductor, so a pure semiconductor is also known as intrinsic semiconductors. Okay, so in a pure or intrinsic semiconductors, the number of holes equal the number of electrons. Okay, so the electron hole pairs is created by the movement of valence electron. And when we are talking about valence electron, we are talking about the electrons that are found on the outermost shell, okay, of the atom of an element. Okay, also in a pure semiconductor, the drift velocity of the electrons is greater than that of the holes. Now let's discuss about the effect of temperature on semiconductors. Okay, but we are going to be comparing it with that of pure metals. Okay, so the electrical resistance of pure metals increases, okay, with temperature rise. That is, as temperature increases, then the electrical resistance of pure metals increases. Okay, but that is not true for a semiconductor, okay? So which implies that the conductance of pure metals decreases with temperature rise, okay? But in the case of a semiconductor, the electrical resistance of a pure semiconductor decreases with temperature rise, which means that the conductance of a pure semiconductor increases with temperature rise, okay? So let's move to the next slide. Now, let's talk about the types of semiconductors. So basically, there are two types of semiconductors, namely the N-type and the P-type semiconductors, okay? So both types are impure semiconductors, which conduct better than the pure semiconductor, okay? So you can't get a pure N-type or P-type semiconductor. So whenever you see N-type semiconductor or P-type semiconductor, basically you are referring to an impure semiconductor, okay? Now let's discuss these types one after the other. So let's begin with the N-type semiconductors, okay? So in an N-type semiconductor, the negative charge carriers are greater in number than the positive charge carriers. Conduction is due mainly to negative charges, that is mainly due to electrons, which are, in this case, which are the majority carriers, okay? While the positive carriers, that is the holes, are the minority carriers in the case of N-type semiconductor. So this N-type semiconductor is produced by introducing a tiny amount of impurity to a pure semiconductor, and the process of adding the impurity is what is referred to as doping, okay? So an N-type semiconductor can be produced by doping pure germanium crystals with arsenic or antimony, okay? And the result of the doping is the production of more free electrons, okay? Now let's move on to talk about the P-type semiconductor. So in a P-type semiconductor, the positive charge carriers, that is the holes, are greater in number than the negative charge carriers, that is the free electrons, okay? So in this case, the holes are the majority carriers while the electrons are the minority carriers. So let's move to the next slide, okay? So this P-type semiconductor, it is produced by doping pure germanium or silicon crystals with an impurity such as indium or boron. The result of the doping is the production of an impure semiconductor with more holes than electrons, okay? So basically, to differentiate between the two types is very easy. P-type means you have more holes than electrons. N-type simply means you have more electrons than holes. So it's as easy as that. Now let's talk about the types of impurity. That is the types of impurities that can be used to dope a pure semiconductor. Now remember that the essence of doping a pure semiconductor is just to increase the electrical conductivity of that semiconductor material, okay? So there are two types of impurities, okay, that are used in doping a pure semiconductors, namely donor impurities and acceptor impurities. Now let's discuss about them one after the other. So let's begin with donor impurities. So donor impurities are atoms of elements with 5 valent electrons. That is, they have 5 electrons on their atomos shell, okay? Now, after a covalent bond with a pure semiconductor of 4 valent electrons, 1 electron is left over. This electron, which is loosely bound, moves about through the semiconductor as a conduction electron. Thus, a donor impurity contributes conduction electron to the semiconductor without contributing holes. So this is also worth taking note of. So the donor impurities only contribute electrons, okay, without contributing holes, right? So examples of donor impurities are arsenic and antimony, okay? Take note that these elements, they have 5 electrons on their atomos shell. So once they finish the covalent bonding with the semiconductor material, 1 electron will be left, and that electron is free to move about as the conduction electron, okay? Donor impurities give rise to N-type semiconductors. Why? Because they simply contribute electrons, okay, when you use them to dope a pure semiconductor, okay? So let's move to the next slide. Now, on the next slide, we are talking about the second type of impurity, which is called the acceptor impurities. Okay, so the acceptor impurities are atoms of elements with 3 valent electrons, meaning that they have 3 electrons on their atomos share. Okay, so in the bond between the pure semiconductor and the acceptor atom, there is a vacancy. Thus, the acceptor impurity increases the number of holes without contributing electrons. So example of acceptor impurities are indium, which is spelled INDIUM, and boron. So acceptor impurities give rise to p-type semiconductor, and the reason for that is because they have 1 electron, okay, on their atomos share less than that of the semiconductor material. So after the covalent bond, there will be a vacancy. There will be a vacancy for 1 electron, which is not there, and that gives rise to hole. Okay, so now let's talk about the p-n junction diode. Okay, so the p-n junction diode is formed when a p-type semiconductor is joined to an n-type semiconductor to act as a single semiconductor. So in that case, the resulting semiconductor is called p-n junction. Okay, so the diagram below is the circuit diagram of a p-n junction, and we also have the symbol of the p-n diode, okay, which is the diagram above the circuit diagram. So what you are seeing on the board here is the circuit diagram of a p-n junction diode. So let's move to the next slide to talk more about it. Now, a p-n junction is said to be forward biased. Okay, so a p-n junction can be said to be forward biased or reversed biased. Okay, so a p-n junction is said to be forward biased when the positive terminal of a battery is connected to the p-type and the negative terminal is connected to the n-type. Okay, so this is a typical this is the circuit diagram of a forward biased p-n junction diode. Okay, so under this arrangement, the positive terminal of the battery repairs the hole. Now take note, remember that for the p-type semiconductor, we have more holes, right? And that part, okay, is connected to the positive terminal of the battery. So in that case, the holes, okay, the positive terminal of the battery will repair the holes towards and across the junction, while the negative terminal repels the electron towards and across the junction. So the effect of this is that the potential barrier, okay, between the p and the n-type materials is reduced, paving way for good conduction, and high current will flow in that case. Okay, so a p-n junction, like I said earlier on, can also be said to be reverse bias. Okay, so a p-n junction diode is said to be reverse bias when the negative terminal of a battery, let's move to the next slide, when the negative terminal of a battery is connected to the p-type, okay, and the positive terminal is connected to the n-type. So this is the circuit diagram of a reverse bias diode. Okay, so under this element, the negative terminal of the battery attracts the hole. Remember, unlike charges attract, okay, and like charges repel, right? So under this arrangement, the negative terminal of the battery attracts the holes, okay, away from the junction, while the positive terminal attracts the electron away from the junction, and this will increase, okay, this will increase the boundary, okay, between the two materials that are joined together to form one. So the effect of this is that the potential barrier is widened, is increased, okay, and this in turn reduces the flow of current. Okay, so in this case, the current flow is extremely small. Okay, now let's talk about junction diode characteristics. Okay, so when the current I is plotted against the applied voltage V, okay, apply potential difference V for both the forward, let's move to the next slide, for both the forward and reverse bias on the same axis, the characteristic graph is as shown below. Okay, so this is the graph, okay, when the current, okay, and then the potential difference across the forward and reverse bias are plotted on the same axis. So this is the graph. This is the graph you obtain. So the graph obtained does not follow Ohm's law, right? Therefore, the junction diode is an example of ohmic conductor like the thermonic diode. Okay, now let's talk about the application of the p-n junction diode. One, they are used in rectifier circuits because of their unique ability to conduct current in one direction. Let's move to the next slide. Two, they are used as signal diodes in communication circuits. Now let's talk about the advantages of the p-n junction diode over the thermonic diode. One of them is that the p-n junction diode is much smaller than the thermonic diode. Two, it needs only a small potential difference to operate in a radio receiver. Three, it requires no time to warm up to produce the current carrier since these are already available in the semiconductor. And four, it is cheaper to manufacture in large numbers. Then five, it is less liable to break, okay, than the thermonic diode. Now let's talk about rectification / rectifier circuit. So basically we are just going to be looking at the meaning of rectification. Okay, so rectification is the process of converting alternating current, okay, to DC current. So a rectifier circuit is a circuit in which an AC input voltage is converted to a DC output voltage. Okay, and the device which makes this possible in the circuit is the junction diode. Okay, so this is where we draw the curtain for the preview of today's video. I believe you enjoyed it, but you can enjoy the complete video by simply clicking on the link in the description below, and that will take you to my school website. On my school website, you will have to subscribe to enjoy the complete video. So in the complete video, we will discuss more about rectifier circuits and their waveform. We'll show the diagram. Then we'll talk about the transistors, and we'll also talk about logic gates, their symbols, and the truth table. Of course, we round up the lesson by answering some worked examples. Okay, so I believe you enjoyed the preview of the video you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly tap on the notification bell to get informed as soon as we release the next videos.